Inverse variation is a relationship where as one variable increases, the other decreases, but the relationship is nonlinear. And so our equation, therefore, is going to be a little bit different. Instead of y equals k times x like it was for direct variation, we're going to have x times y equals k, or y equals k over x is an alternative if we just divide both sides by x. And so in this way, if we imagine that the product of the two variables is going to equal some constant k, well, as I plug in larger and larger values for x, I need to compensate for that with smaller and smaller values for y in order to maintain the same constant value k, our constant of variation. But beyond the nature of the relationship and the different equation type, our approach to these types of questions is going to be very much the same like it was for the direct variation. So in this circumstance here, we're given A varies inversely as B. So that, again, has to be stated openly for us. So we know we're looking at A times B equals K. And so then we've got some information about the two values for that were a pair together for this particular example. So we've got 12 times 2 equals K. So we know that K equals 24. So for this problem, our constant of variation is 24. So our model equation, therefore, is A times B equals 24. And so now we can use this model equation with the second part of the problem where it says we want to find A when B is 6. So it's as easy as A times 6 has to equal 24. So if we divide both sides by 6, we get A equals 4. In the second example, we again are given explicitly the information about the variable relationship, have to have that there. R varies inversely as T, so I can start with R times T equals K. I've got my given information about the relationship between the variables, so 27 times 1/9 equals K, so that means my constant in this case is going to be 3. So now my equation, or my model equation, RT equals 3 is what I'm going to use for the last part of the question. So we want to know what is R when T equals 3. So obviously R has to equal 1. Finally, we can have more than two variables involved in a relationship. And so the first scenario we see here is where there's a mixture of both direct and inverse variation in the same question. So we call that a combined variation circumstance. So in this example here it says that A varies inversely as B and directly with the square of C. So if we think of what our inverse relationship with B would look like, if that was all we had, it would be A times B equals K. And then if it was just A is varying directly with the square of C, well, that would be K times C squared. So here we have the relationship mapped out. So we just have to interpret what's given to us about the relationship between those variables. And so now we're going to proceed the same way that we did before. Got to find what K is first. So we're going to replace A with 16, B with 24, equals K times C squared. So that's going to be 2 squared. So that's 4. So I'm going to divide both sides by 4. And so we get a K value in this case of, if I reduce here the 16 and the 4, I just have 4 times 24 left, so I get 96. So my model equation is going to be AB equals 96 C squared. So we've got our model, and now we can use it for the last part of the problem. So we want to find B when A is 12, so I'm going to have 12B equals 96 times, and we're told C squared is, or C is 9, so 9 squared. So I'm going to divide both sides by 12, and so we get B equals, now again I'm going to do a little reducing, so the 12 divides into 96 8 times, so I'm left with 8 times 9 squared. Well, 8 times 81 gives me 648. And in the last scenario, we have what's called joint variation, where everything is direct with the initial variable. So if it says z varies jointly as x and y, that is implying that it's z equals k times x times y. So it's direct variation for z with both of those variables. So now again, our first task is to find what k equals using the information given here. So we've got 4 equals k times 20 times 3. 20 times 3 is 60, so I'm going to divide both sides by 60, and so we get a k value of 1/15 if we reduce. So our model equation is going to be z equals 1/15 times x times y. So we got that here, and now we'll make use of it for this last part of the problem. We want to find x when z is 12, so that equals 1/15 times x is our mystery value, and then times 18 for y. So I'm going to multiply both sides by 15, and at the same time I can go ahead and divide by 18. So if we do a little bit of reducing here, the 18 and 12 both divisible by 6, so I can replace that with a 2, that with a 3, and then 15 and 3, I can reduce that. The 3 goes, 15 becomes a 5, so then we're all left with x equals 5 times 2, so 10.